Okay, so today we're diving into this pretty heated debate actually going on in the quantum computing world.
Yeah, some real drama.
Yeah, right. It all starts with this paper from Microsoft Quantum.
Published in Physical Review B.
Yep, and they're making some big claims.
Yeah, they say they've found evidence for Majorana-bound states.
Which, if you're not familiar, those are...
Quasi-particles.
Yeah, and the thing that makes them so special is...
They're their own antiparticles.
It's kind of mind-blowing, right? I mean...
It is, yeah, and it has huge implications for quantum computing.
Because...
If you could actually harness these Majorana-bound states, you could potentially build much more stable qubits.
And that's...
That's kind of the holy grail right now for quantum computers.
Totally. Yeah, like the qubits we have now,
they're super fragile.
Super fragile, yeah. It's like trying to...
Like building a house of cards in a windstorm.
Exactly.
Yeah.
Yeah, the slightest disturbance and the whole thing falls apart.
And that's a major roadblock for building practical quantum computers.
So finding these Majorana-bound states would be a huge deal.
They would be a game changer.
But now we have this guy, Henry F. Legg.
Yeah, he published a comment on the Microsoft paper.
And he's basically saying...
Not so fast.
Yeah, he's like, hold on a second. Let's take a closer look at this evidence.
He's specifically questioning the method they use to analyze their data.
Which is called?
The Topological Gap Protocol.
Or TGP for short.
Right. And the TGP is all about analyzing the conductance data from these nanowire devices.
So these are like...
Tiny, tiny wires.
Yeah, we're talking nanoscale here.
And the TGP looks for specific patterns in the conductance data.
These patterns are called gaps.
And they're supposed to be like a fingerprint for Majorana-bound states.
So Microsoft is saying, we see the gaps, case closed, we found them.
Right, but Legg is arguing that those gaps might not be what they think they are.
He's saying the TGP itself might not be as reliable as everyone thinks.
Exactly.
So what's he basing that on? What are some of his specific criticisms?
Well, for starters, he points out that the way Microsoft defines a gap in their code...
In the actual software they use to analyze the data.
Right. It's different from how they describe it in the paper.
Oh, so there's a discrepancy there.
Yeah, and that makes the whole analysis really sensitive to the specific parameters they choose.
So like if they tweak the settings a little bit?
It could change whether they see a gap or not.
That's not good.
No, it's not. And to make matters worse, Legg found that some of these key parameters varied a lot between different measurements in their study.
Like what kind of parameters?
Things like the range of magnetic fields they used and the bias voltage range.
So basically they weren't being consistent in how they were collecting the data.
Right. And those inconsistencies can directly impact the outcome of the TGP analysis.
So what they're claiming is a Majorana fingerprint.
Might actually just be an artifact of how they were setting up the experiment.
That's kind of like saying you found a new species of butterfly.
But the pattern on its wings was just a smudge of dirt.
Yeah, exactly. So it's not a real discovery, it's just a mistake.
Right, and Legg also points out another problem.
Okay, what's that?
There's a discrepancy between how they applied the TGP to theoretical simulations and how they used it on the actual experimental data.
So they're not even being consistent in how they're using the tool itself.
Right, and this involves something called the average overcutter parameter.
Average overcutter? What in the world is a cutter?
So basically you have these multiple probes measuring the nanowire's conductance at different points.
Like tiny needles.
Yeah, you can think of them as needles, and each probe is called a cutter.
Okay.
And the average overcutter parameter decides whether you average the signals from all the cutters.
So you're either looking at the individual readings from each cutter,
or you're combining them all together.
And that choice can affect the results.
It can significantly affect the results, yeah.
So they might be seeing gaps that aren't really there.
Just because of how they're handling this cutter data.
And that calls into question the whole idea that the TGP is this reliable test for topological superconductivity.
Right, it's supposed to be this definitive test.
But Legg is saying it's a lot more nuanced than that.
Much more nuanced.
So this is getting pretty complicated.
It is, yeah.
But it sounds like Legg is raising some serious concerns.
He is, yeah. And it's going to be interesting to see how Microsoft Quantum responds to his critique.
Yeah. I'm curious to hear what they have to say.
Me too.
Because if Legg is right, this could have big implications for the whole field of Majorana research.
Absolutely.
And for the future of quantum computing.
It could change everything.
So stay tuned. We'll be right back after the break.
And there's another layer to this whole thing, too.
Oh, there's more.
Yeah, so Legg also points out that Microsoft kind of redefined what topological means in their simulations.
Wait, so they're changing the definition of a key term.
Yeah, essentially they loosen the criteria for classifying a region as topological.
And why is that a problem?
Well, it makes it hard to compare their simulations to their actual experiments.
It's like they're moving the goalposts.
Exactly, and it raises questions about whether their simulations are really reflecting what's happening in the real world.
Okay, so we've got inconsistencies in how they define a gap, inconsistencies in their experimental parameters, and now they're redefining what topological even means.
Yeah, it's a lot to unpack.
It really is. But let's try to step back for a moment and think about the bigger picture here.
Okay.
What are the implications of all this? I mean, if Legg is right and the TGP isn't as reliable as we thought...
Well, it could mean that some of the evidence for Majorana-bound states that's been reported in other studies might need to be reevaluated.
So we're talking potentially years of research being called into question.
It's possible, yeah, but it doesn't necessarily mean all those findings are wrong.
Right, it just means we need to take a closer look.
Exactly, we need more rigorous and independent verification.
Which ultimately is a good thing for science, right? I mean, this kind of critical examination, even if it's disruptive, it leads to a more robust understanding.
Absolutely, science is all about constantly questioning and refining our knowledge.
And Legg's critique is definitely forcing us to do that.
It's a valuable contribution to the field, even if it's challenging some deeply held assumptions.
It's also a good reminder that even in a field as cutting edge as quantum computing, we can't get carried away by the hype.
Right. We need to stay grounded in solid evidence and rigorous analysis.
Extraordinary claims require extraordinary evidence.
And the claim of observing Majorana-bound states is definitely extraordinary.
So what happens now? I mean, is there any way for Microsoft to address these concerns?
Well, Legg's analysis was based on the data and code that Microsoft made publicly available.
Right.
So it's possible they have additional data that hasn't been released yet.
Data that could support their claims.
Or data that could refute them.
So we're kind of in a waiting game to see if they respond.
Yeah, and it would also be interesting to see if other research groups try to replicate these findings.
Using the TGP or maybe even developing new methods for detecting Majorana-bound states.
Exactly. Independent verification is crucial.
This whole debate also raises some interesting questions about peer review.
Oh, yeah, for sure.
I mean, how did a paper with these potential flaws get published in the first place?
That's a good question. Peer review is supposed to catch these kinds of issues, but it's not a perfect system.
Especially in a field as specialized as this one.
Right. There might only be a handful of people in the world who are qualified to really scrutinize this kind of work.
So maybe we need better mechanisms for post-publication review.
I think that's becoming increasingly important, especially with preprints becoming more common.
Where research gets shared before it's officially published.
Right. It allows for a wider range of perspectives and expertise to weigh in.
It's like crowdsourcing the scientific process.
In a way. Yeah, and that can only be a good thing.
More scrutiny, more debate, ultimately leads to better science.
Exactly.
Well, this has been a fascinating discussion so far.
It has.
We've gone from the mind-bending world of Majorana-bound states to the nitty-gritty details of the Topological Gap Protocol.
And the importance of scientific debate.
It's been quite a journey.
A journey that's not over yet.
That's right.
Yeah.
There's still a lot we don't know about Majorana-bound states.
And about the TGP and how to best use it.
But that's what makes science so exciting.
The pursuit of knowledge, the constant questioning, and the willingness to challenge even our most cherished beliefs.
Well said. So to all our listeners out there, keep those minds curious and keep those questions coming.
We'll be back next time with more deep dives into the latest scientific breakthroughs.
It's quite a challenge though, right? I mean, if the TGP isn't reliable, what other options do we have?
Well, we need a more direct way to probe the unique properties of Majorana-bound states. And one promising avenue is exploring their non-abelian statistics.
Non-abelian statistics. Now, that sounds complicated.
It is a bit mind-bending, but basically it means that when you swap the positions of two Majorana-bound states, their quantum state changes in a very specific way.
Okay.
It's unlike anything we see with ordinary particles, like electrons or photons.
So it's a fundamentally different way these particles behave.
It's exactly.
And that could be the key to proving their existence once and for all.
If we can design an experiment that clearly demonstrates this non-abelian behavior, it would be a smoking gun for Majorana-bound states.
It would be like finding their unique fingerprint.
Right, not just some blurry image that could be interpreted in different ways.
So what would that experiment look like?
There are some interesting ideas out there.
Like what?
One proposal involves manipulating Majorana-bound states in a way that creates specific quantum interference patterns.
So we're talking about controlling these particles at a very precise level.
Yeah, and the patterns would only arise if the particles are truly exhibiting non-abelian statistics.
So it's like setting up a tiny obstacle course for these Majoranas.
And seeing if they behave the way the theory predicts.
Exactly.
It's a very challenging experiment, but if it works, it would be groundbreaking.
It's amazing to think about the level of precision and ingenuity that's required for this kind of research.
It really is pushing the boundaries of what's possible.
And it just shows how important this whole debate is.
Yeah, it's not just about proving or disproving one particular claim.
It's about pushing the entire field forward.
Exactly. And Legg's critique, even if it's uncomfortable in the short term,
could lead to even more innovative approaches in the long run.
I think that's a very good way to put it.
It forces us to rethink our assumptions and develop new tools.
And that's how science progresses.
Well, I think we've covered a lot of ground today.
We have. It's been a fascinating discussion.
From the theoretical wonders of Majorana-bound states
to the very practical challenges of actually detecting them.
And the importance of open scientific debate.
It's been a real deep dive.
It has. And it's a reminder that even in the most cutting-edge areas of science, there's always more to learn.
Always more questions to ask.
Always more mysteries to unravel.
And that's what keeps us coming back for more.
That's the beauty of science, the constant pursuit of knowledge, the thrill of discovery.
I couldn't have said it better myself.
So to all our listeners out there, keep those minds curious and keep those questions coming.
We'll see you next time for another deep dive into the world of science and technology.
Until then, happy exploring.